So we are in the session W15, built environment and urban mobility pattern. So good afternoon, everyone. I assume that you're in different time zone. We are afternoon, so welcome to our session. My name is Mohammad Miradi Naqi from the Illinois Institute of Technology. I will be chairing this session. Today we are really joined by diverse and well-known researchers around the world, uh, ranging from different countries, Brazil, Mexico, United States. It shows the importance of the built environment and emerging technologies, the way that they reshape the transportation technology. So we have a broad set of studies today addressing key themes in the mobility patterns and urban planning. So we'll start with a comprehensive review of how the built environment influences the transport dynamic. We will then explore novel perspectives on urban congestion, vehicle diffusion trend in the US, and patterns in online delivery and returns. We'll also hear about the use of Street View data for walkability audits near public transport stations in the global south, and we'll close with an innovative application of vision language models for vehicle surveillance. So each presenter will have 15 minutes, followed by 5 minutes for Q&A. Please be careful about this allocated time. Maintain a smooth session and allow for a meaningful discussion. So, do we have Raphael?
Okay, perfect. Good. So good afternoon, good evening, and good morning, everyone. My name is Rafael Pereira, and I work at the Brazilian Institute for Applied Economic Research. And I'm presenting today a paper or a study that is still under review. And this is a study I'm doing with colleagues from IPEA and the University of São Paulo. And the study is actually a very simple idea. So we're trying to rethink congestion as lost accessibility. So to set the ground scene, we know that congestion is a very pervasive issue across the globe for many large scales, mid-size and large cities. Pretty much every large city in the world has some congestion problems. The problem, however, is that congestion is typically assessed from a mobility perspective and using traffic performance measures, right? So if we look at the transportation and transport engineering manuals, widely what we will see is that we have been measuring transportation congestion using traffic performance measures such as speed reduction index or travel time delays or traffic throughput. So basically, the main idea behind this indicator is that for a given road segment, you measure what is the average speed of the cars going through that road segment during the peak time and during the off-peak time, and the congestion is the difference between those. In some indicators, we use the speed of the vehicles or the travel time that would take you to traverse a certain distance, or the number of vehicles per given amount of time. But generally, this is a very traditional transportation engineering kind of mobility perspective. And what these indicators look like is basically like this. So generally, the traditional data of congestion, when we map those data sets, this is the kind of figure that we have. So we know the roads that are congested or that have lower traffic speeds because of the streets are clogged. But if you really look at those maps, you know the road segments that are congested, but you don't really know the people who are stuck in traffic, where they come from, where they live, what are their social demographics. So a main limitation of this mobility-based understanding of congestion is that it's not really possible to tell who is the group most affected by congestion. So it gives us a blind understanding to the distributional effects in terms of what groups are more or less affected by congestion. And what we aim with the study is really to propose a simple reframing of congestion as lost access to opportunities due to excess time in traffic. So we're not thinking about congestion merely as a problem of slower speeds and longer travel times, but we're trying to understand to what extent those slower speeds and longer travel times actually affect and deplete people's ability to access opportunities across space. So put it simply, we're simply measuring congestion by looking at how much of our accessibility drops if you're traveling during the peak time versus off-peak time with free flow conditions. For this specific paper, we're trying to demonstrate this idea with a comparative study looking at the 20 largest cities in Brazil. We are looking specifically at congestion effects for car accessibility. To do this, we're using historical road speed from Street Map Premium from Esri, and we are doing the routing analysis with Network Analyst ArcGIS. For the off-peak time, so basically we need to calculate some travel time matrices. So how long does it take you to travel by car from each city block to every other city block at different times of the day? So for the off-peak, we're calculating a single travel time matrix departing at 4 a.m. on a weekend. And for the peak time, we look at business days and we calculate multiple travel time matrices departing every 15 minutes from 6 a.m. to 8 a.m. And then we take the median travel time of the peak period. So once we have the travel time matrices, we also need to calculate accessibility. We could think of dozens of different accessibility metrics to use, but for various reasons that we discuss in the paper, in this study, we are using the time interval cumulative accessibility measure. So most people here who are familiar with the accessibility literature, we are very familiar with the cumulative accessibility metric, where we calculate, for example, the number of jobs you can reach within, let's say, 20 minutes. The problem with this traditional cumulative accessibility metric is that you have to choose a single cutoff travel time. And the idea of the time interval cumulative accessibility metric is that instead of choosing a single cutoff travel time, you choose a time interval, let's say between 15 minutes and 45 minutes. That's what we're doing here. So what this indicator does is it calculates the average number of opportunities that you could reach within a given travel time interval. So we're basically calculating multiple cumulative accessibility metrics minute by minute within that interval. This sounds like a very simple adaptation to the cumulative metric, and it is a very simple adaptation. But the big advantage that we get of this out of this indicator is that it overcomes the boundary effect of the modifiable temporal unit problem. So this indicator was proposed by myself and colleagues in a paper we published recently in Applied Geography. And basically we demonstrate in that paper that when we use the time interval cumulative metric, we kind of protect ourselves by the fact that the arbitrary choice of your travel time threshold or your arbitrary travel time interval could affect your results. So depending on the time threshold you use for your traditional cutoff of cumulative metric, your accessibility results can vary a lot. With the time interval, regardless of the time interval you choose, your results will vary very, very little. So the results are much more consistent and much more robust. So finally, we combine those travel time matrices and the time window cumulative accessibility metric with some census data and employment data. So we have the spatial distribution of individuals, social demographics, and jobs for all of those Brazilian cities. And here are the quick main results, okay? So the first result is just, we were wondering how the ranking of congested cities would change. So it's very common to see on newspapers, the governments want to rank or compare what cities are most congested, right? So we are comparing the ranking of the most congested cities if we measure congestion looking at accessibility losses, average commuting time, or a traditional traffic speed index, here the one that's calculated by the global company TomTom. And just looking quickly at this chart to see a very, very marked differences in how the rank changes between these indicators. And the reasons for this are basically some fundamental methodological differences between these three approaches. So the speed index that's used by TomTom and the traditional transportation engineering methods to measure congestion, the problem with that indicator is that they don't account for population. So you know how many roads are congested and by how much, but you don't know how many people are actually affected or because they're trying to traverse that road segment. So this is not really weighted by population. Commuting time estimates, on the other hand, you know how much time people would spend on their commute, but you don't really know the distances they're traveling. So this is not really a good measure of congestion because it doesn't really account for the performance of the system. The accessibility metric, on the other hand, it does account at the same time for travel speed, for travel distances, and for population, but it doesn't account for travel behavior because accessibility, as you know, is fundamentally about potential access to opportunities. So these are three fundamental differences, but accessibility, although it does not account for travel behavior, or it only accounts for potential accessibility, it's really suitable in the sense that it accounts for all of the three dimensions at the same time: speeds, distances, population, in a way that integrates transportation and land use. So this is just a ranking. If we look if we dive more deeply into the accessibility estimates, this is how congested Brazilian cities are. So in a city like São Paulo, for example, on average, people access approximately 48 to 50% less jobs during the congestion time compared to free flow. So basically, their congestion level is 50%. They lose access to half of the jobs they could access just because of congestion. In smaller cities like at the bottom of my chart in Campo Grande or São Gonçalo, this gets to less than 5%. The interesting thing about this measure of congestion as accessibility is that because we are able to measure people's socioeconomic characteristics about where they live and how their accessibility changes during congestion, we can actually unpack this chart into a more interesting chart where we see the differences by socioeconomic groups. So here, yellow dots are the wealthiest neighborhoods in the city, and the blue dots are the poorest neighborhoods in the city. So we actually see that even in São Paulo, where it's an extremely congested city, high-income individuals in São Paulo roughly lose only 20% of their access to jobs because of congestion. While for the poorest population, this congestion levels gets to almost 60%. And naturally, we see various differences. You know, in some cities, the accessibility gap between the rich and the poor becomes much wider because of congestion. So there is great heterogeneity in how congestion is experienced by different socioeconomic levels. On average, for all of the Brazilian cities, the wealthiest population lose 5% of their access to jobs because of congestion, while the poorest people lose 25% roughly. And in a city like São Paulo, as I said, this goes from 20% to 56%, which is a very startling difference in how these different groups are affected by congestion. So it's almost as saying that the poorest people are twice as much affected, or more than twice as much affected by congestion than the richest population. If we look at this spatially, the maps here we have on the left are on the top, you see the city of Fortaleza, and on the bottom, you see the city of São Paulo. This is how many jobs you would be reaching by car during free flow. And you can see that for Fortaleza, you can pretty much access almost all of the jobs from almost everywhere in the city, while São Paulo is a much more extensive and large city, so you get a more heterogeneous distribution. During peak, naturally, these accessibility levels, they drop quite substantially, especially in the peripheries and in the city center. And when we check the relative difference between the peak and off-peak, that's what we're calling our congestion impact on accessibility. This is the picture that we have. And I think I would like to stress only three key takeaways here in this chart. The first one is that there are very marked spatial heterogeneities in how accessibility is affected by congestion, or how congestion manifests itself in terms of lost access to opportunities. The interesting thing to start with is that the most affected areas by congestion are not necessarily where the roads are more clogged. So you see here in the city of São Paulo, the darker toned colors are places where you have lower congestion impact on accessibility. So basically, you lose relatively less access to jobs because of congestion than in these areas with very bright colors. So if you look at the traditional mobility-based congestion, you would think that the most congested part of the city is in the city center or in downtown. And what we're showing here is in fact that in the city center, that's where you lose very little access because of that congestion. And the main reason for this is that areas near the city center are pretty much very close to jobs. So you have very higher concentration of jobs near the city center. And because you have that big proximity between people and activities, even if you are facing congestion, you only need to travel very shorter distances to reach those activities. So the congestion will affect you, but very, very little. The other thing is that the city center becomes an impermeable to those that are outside. So if you're inside the congestion or where the roads are clogged, but you only need to travel very short distances to reach jobs, you're relatively fine. However, if you're outside the city center and you need to go into the city center to reach those jobs in there, it becomes almost impossible to penetrate the city center because those streets are clogged. So the people who are actually most affected are not people living in the near clogged streets, but those who are nearby or surrounding the city center. And finally, those who are really at the fringes. If you look at the extreme east zone of São Paulo or the extreme south zone of São Paulo, you see that those areas have relatively lower impact of access. And that's because they're so far away from the city center that even with free flow conditions, they would not be able to reach the city center in a reasonable amount of time. So just to close my presentation, there are, I think, 3 key takeaways that I'd like you to take with this. What we are proposing is a shift we're proposing that we shift how we understand congestion from a mobility perspective to use an accessibility lenses. And the main advantages of this shift or this paradigm shift is that this aligns with a growing body of work that advocates for accessibility-oriented planning instead of mobility-oriented planning. We should think about how we plan our cities and land use systems and transportation systems to maximize and improve access opportunities and not so much tackle congestion. And there's a growing body of very good research that it's going this direction. And I think this paper goes with that flow in that vein. The second takeaway is that this paradigm shift provides a comprehensive assessment of how urban congestion, provides a comprehensive assessment of urban congestion that considers the interaction between transportation and land use systems. So we are not simply looking at the transportation system isolated from people and from the land use, but we're actually looking at how those things are interconnected and integrated. And finally, and perhaps the most important point of this study is that we showed that from an equity standpoint, changing your focus to look at congestion from an accessibility perspective helps us identify how the diverse effects of congestion are actually distributed across socioeconomic groups. We can know with this kind of approach what neighborhoods and what socioeconomic groups are more or less affected by congestion. So if you're interested in this study, this is currently under review, but the preprint is already available online. You can have a look at this website here on the link. And with that, I close my presentation. I'm very happy to take any questions you may have.
Thank you. Any question from audience? We have some question in the chat box. Can you read the chat box and answer those questions?
Okay, there is one question from Serhi. Hello, Rafa. Thank you for your presentation. Can you speak more about the choice of the accessibility metric? What other metrics have you considered, and what pros and cons are there? How is time interval is exactly better than a fixed time threshold? So basically, ideally, we might want to run a second round of analysis considering, let's say, gravity-based accessibility metric. The problem that using a gravity-based accessibility metric here is that it would be very hard to define or to choose what would be the decay function or the parameters that how we would calibrate, considering that different cities we're looking at cities of very different sizes. So the decay functions, if you look at the travel behavior data, they would have very different parameters, and using a single decay function would allow cities to be comparable, but it would not represent travel behavior. So using a gravity-based model would be very tricky for these reasons, right? So travel behavior differs. The calibration of the parameters would be very difficult. The time interval accessibility metric basically differs from the traditional cutoff accessibility metric because we're not calculating a single accessibility metric for one cutoff. We're calculating multiple metrics for various cutoffs minute by minute within the time interval. And the advantage of that is, as I mentioned in my presentation, is that if you only use one travel time cutoff, your results become very, very sensitive to the cutoff you choose. So there is a very large risk that you might be, cherry picking the travel time threshold that gives you the result that you want or the result your intuition would expect. By using a travel time interval, we are actually protecting ourselves from this, and we are using a much more robust approach that regardless of the travel time interval you use, which is also arbitrary, but regarding of that arbitrary choice, your results are much less affected by the time interval that is selected for the analysis. So that's really the main advantage of this, is that we overcome the modifiable temporal unit problem here.
Great, thank you. Thank you for presentation. So the next speaker would be Saba Ayub. So I know that we have the recording. So the presentation would be on the on the exploring the impact of the built environment on urban mobility patterns and advanced transport dynamics. Thank you.
Hello, I'm Dr. Sabha, and today I am here to present my systematic review on exploring the impact of the built environment on urban mobility patterns and advanced transport dynamics. Here is the list of content. Following by the introduction, I will present the methodology part, and after that I will present the area reviewed in this article, and later I will discuss about the discussion, and at the end conclusion will be presented. Here is the introduction part. As road crashes cause many injuries and death globally, the World Health Organization estimates that 1.35 million people crash annually in traffic collision. Transportation is a noteworthy contributor to greenhouse gas emissions and ultimately play a central role in the economy and society. Autonomous driving solutions have been implemented in recent years as part of the wise and balanced transport agenda. Fully autonomous on-road vehicles have the potential to generate a various exhibit of social and environmental advantages if they are powered by a pure implement system. Among the several uses of autonomous cars, shared autonomous vehicles emerge as a notably promising breakthrough. Shared autonomous vehicles integrate a self-driving technology with shared mobility principle, presenting a novel example for urban transportation that might improve efficiency, moderate blocking, and diminish environmental concerns. With significant effect on the sustainability and development of the city, these phenomena might affect the general performance of public transport networks. Travel behavior research uses a range of techniques to investigate both behavioral and sociological surveys, interview and case studies, and economic optimization, modeling, simulation, and forecasting aspects. So this paper will investigate the multifaceted effect of public transport on travel behavior and study various factors that contribute to environmental impacts. Our objective is to offer a delicate conception of the potential advantages and obstacles that may arise from the integration of transport into modern transportation system by analyzing these factors, assessing how various aspects of the built environment including density, variety, and design influence travel behavior. It also examined the influence of emerging technologies in mobility modes and trends such as the propagation of shared mobility services and the movement towards smart cities in transforming conventional examples. This study aimed to clarify the existing state of knowledge to guide future research and policy activities focused on promoting sustainable urban mobility and enhancing community livability. Here is the methodology part where Prisma statements were used to design the methodology and divided into 4 phases: identification, screening, eligibility, and included. In the first phase, identification, initial search from Scopus database, I got 274 articles. After that, the record after duplicates, I go through the screening phase where I remove on the basis of title screening, and I got 140 articles. And after that, some paper were excluded after abstract screening, and final interpretation of study, I got 62 number of articles, and in the end included studies in the data section is 61, where 3 articles were removed on the basis of that content does not fit in this study scope. Here is the distribution of article on yearly basis. You can see green color represent here journal papers and pink color represent the conference papers. So here this figure shows the network visualization of keyword co-occurrence, and you can see I got more articles on the built environment, travel behavior, urban transport, and public transport. Here you can see the network visualization of co-authorship. Mainly 5 authors I got which published a lot of data on these areas, and there have been no connection between them. So here is the area reviewed. The finalized 62 articles were divided into specified sections for better interpretation and reviewing process. So here is the 5 sections I have mentioned, mainly which were focused: built environment and cycling, transit and multimodal integration, travel behavior and mode choice, ride hailing and other services, and at the end, environmental impact and urban planning. Here is the discussion about this article. The research emphasized the complex and diverse relationship between the built environment and travel behaviors, drawing on studies undertaken in a variety of global contexts including Australia, China, Bangladesh, Spain, Germany, and India. To investigate this relationship, a range of analytical methodologies were used, including modern methods such as machine learning and agent-based modeling, as well as standard statistical techniques. The core finding emphasized that certain built environment elements such as infrastructure, quality, transportation network, and land use variety have a major impact on travel pattern. However, the quantity and form of these impacts vary greatly depending on the geographical, cultural, and socio-economic situations. In addition, the literature emphasized the transformational influence of public transport system, particularly rail network, on urban mobility and growth. These systems promote multimodal travel by allowing for seamless transition between modes and transportation, with features like walking distance to metro stations and the presence of bike lanes greatly impacting consumer choice. Here is the conclusion. This systematic review explained the complex relationship between built environments and travel behaviors, reflecting the diversity of global urban perspectives. The outcome established that infrastructure, quality, connectivity, and mixed land use are crucial for advancing active and sustainable mobility. High-density bicycle network and transit-oriented developments promote walking, cycling, and public transit use. Yet their success is often mediated by socio-demographic factors, including income, gender, and vehicle ownership. Furthermore, the advent of mobility innovation like e-bikes and dockless bike sharing system heads both prospective and confront traditional transportation modes. Public transport system, particularly rail network, emerged as revelatory in terms of urban mobility and growth. These solutions not only enable multimodal transport but also boost employment opportunities, increase productivity, and optimize urban area use. However, ongoing difficulties with social equality, accessibility, and the unintentional effects of ultra-dense urban areas demand a balanced approach to design. Thank you so much for listening me. If you have any question, you may ask.
Thank you. Do we have Saba here? So we don't have Saba here, so we can skip Q&A for this presentation. So next presentation would be Hania Afzal on mapping vehicle diffusion dynamics in the United States.
So today I'm going to present my research work on mapping vehicle diffusion dynamics in the United States. Vehicle fleet composition, as we all know, is an important dimension of transportation policy and planning. And diffusion is basically defined in chemistry as the movement of matter from a region of high concentration to one of the low concentrations. So, technology diffusion is a two-dimensional process, which is social diffusion and spatial diffusion. So, social diffusion of technology may occur across socioeconomically similar communities on opposite sides of the country before spatial diffusion occurs to spatially proximate communities, which means like people residing in different parts of the country having the same socioeconomic status may have same preferences for a particular technology or a particular characteristic as compared to the spatial diffusion. So we have basically used the electric vehicle registrations data that has been provided to us by Experian Inclusive. The vehicle registration dataset comprises of a 10-year panel data at 2-year intervals, like starting from 2012, 2014 till 2020, and we have the data for Q4 for 2021. The total vehicle registrations for each vehicle fuel type or category has been recorded by county, make, model, year, and other vehicle characteristics for the United States. Census data has also been compiled to construct the county level statistics for household income and racial composition. We have used the 5-year American Community Survey data to approximate the annual variations. So we use the 2011 to 2015 American Community Survey for the years 2012 and 14, and 2016 to 20 American Community Survey for the years of registration 2016, 2018, 2020. We have also incorporated the income variable and racial minorities variable because these variables often influence the technology adoption patterns. And we have also considered the state grid total carbon emissions as an variable, and understand that how it has affected the adoption. This is a statistical summary of the data, which basically gives us an overview of the different variables that we have used in our analysis. So we have used the percentage of plug-in hybrid electric vehicles. So these percentages are basically the percentage of each particular category of vehicle type as a total as of total registrations. And then we have the county population, similarly, like we have percentage of hybrid electric vehicles, we have fuel cell electric vehicles, US brand vehicles. So US brand vehicles are basically vehicles that have been manufactured in the US. We have county population, percentage of young population in a country, like how youth is contributing towards the adoption of this new emerging technologies, the percentage of minorities. Then we have the travel time. We have the median household income, state grid emissions, and small cars as a percentage of total vehicles in a county. So the main research objective of this study was to understand the spatial diffusion of these different types of vehicle fuel types and US manufactured vehicles for the US from 2012 to 2021. And we also studied the COVID's effect on the adoption of these technologies across USA using the county level data across different counties. We have also analyzed the direct versus the indirect effects, which I'm going to explain a little bit more in upcoming slides. So before even setting up this spatial modeling, we ran some basic diagnostic tests in order to understand that is there any spatial dependencies or there is any spatial relationship available among these in the diffusion of these technologies across USA. So we performed the LM test for spatial dependence in residuals, which indicates that whether spatial autocorrelation needs to be considered in the model or not. And then we have the modernized test for spatial autocorrelation. The modernized spatial test is widely used in spatial statistics and GIS to analyze the spatial patterns. So modernized basically is a measure of spatial autocorrelation, which assesses the degree to which like the similar values cluster in a geographical space. In other words, it helps us to determine if a variable spatial distribution is random, is it clustered, or we are seeing some high clusters or low clusters, and it has its value from -1 to +1, and the value of greater than 0 indicates that there is positive spatial autocorrelation, meaning by that similar values are clustered together, like higher adoption counties are surrounded by the higher adoption counties, or lower adoption counties are surrounded by the lower adoption counties. With a modern I of less than 0, it indicates the negative spatial autocorrelation, meaning by that there is some dissimilar pattern of clusters, like maybe the high adoption counties are surrounded by the low adoption counties or vice versa. And modern I coefficient that is approximately equal to 0 indicates that there is no spatial autocorrelation, or we could say that the distribution is random. So this is my test results for LM test for spatial dependence, and all for all the vehicle fuel types and the US brand vehicles, we got this statistically significant results, which suggests that the adoption pattern of these technologies in one county is influenced by the adoption in the neighboring areas, and they are spatially correlated factors. So that led us to and then we as I discussed about the modern I and the Lisa plot, local indicator of spatial autocorrelation plot. So this is our map for plug-in electric vehicle registration in the US from 2012 to 2021. We have by plotting these figures, we were basically looking at the pattern, that whether we have the similar pattern over the period of time, or how the spatial diffusion has been occurring in each and every year, or is there any change in the clustering of these adoption patterns. So what we observed is, we can see from these figures that California consistently shows that the high cluster. So here high means the counties, high adoption counties of plug-in electric vehicles surrounded by the counties that are also high in adoption. So we see that California is basically is the showing the highest adoption, and also it is influencing its neighboring counties. And if we look at the western and northeastern states, we see that adoption, we see an increasing adoption spatially, and over time this clustering has improved. And if we look at the midwestern region, we see that there is a low adoption, or that is low clusters, which means that there are low adoption counties surrounded by the low adoption counties. So this is the Lisa cluster map for hybrid electric vehicles. And we could see that California and the Coast has continued to lead the HEV adoption with significant high clusters everywhere. These regions likely benefit from state level incentives and the infrastructure development that has been going on for quite some time now. And but the northeastern and southeastern states also see an increase in HEV adoption, particularly if we look at the 2021 LISA cluster map. And if we look at the central states, there is a low pattern showing the persistent low adoption, which may be due to a lack of supportive policies, infrastructure, or maybe people preferring to having preference towards some other fuel type cars. And if we look at the southeast and northeast over time, well, it indicates that an increase in HEV adoption beyond the traditionally strong areas, potentially due to the gradual infrastructure development and changing consumer preferences. So we can see that HEV adoption shows the spatial clustering pattern that is similar to PEVs, with the West Coast as a stronghold and central regions lagging in adoption. The clustering highlights how regional factors such as policies and consumer preferences influences the HEV adoption across the USA. And then we have the LISA cluster map for hydrogen vehicles. Hydrogen vehicle is right now at very early stage of diffusion. So here we see that Southern California consistently appears as the only high cluster from 2018 onwards, highlighting it as a unique region for hydrogen vehicle adoption in the US, likely due to supportive infrastructure and policies. And similarly, we have this LISA cluster map for US brand vehicles, and we see that here the Midwestern region and the southern regions have a strong and stable preference for the US brand vehicles, and it is being evident by the high clusters in each subsequent year of analysis. And we see that West Coast and Northeast regions show a consistent pattern of low adoption for US brand vehicles, possibly due to the higher prevalence of foreign brands or alternative vehicle fuel type popular in those areas. And we see that unlike the other vehicle fuel types, the US brand vehicles remain relatively static over the years, and this static ability indicates that the regional preference for vehicle brands are well established and resilient to changes, possibly due to factors like brand loyalty, economic ties, or market dynamics unique to these regions. These are the Morenai coefficients for each year, and if we see that clustering pattern has significantly improved over time for each vehicle fuel type, which indicates that the P for instance, if we compare the PEV in 2012 to 2021, we could see that this spatial clustering has improved or enhanced over the time. Similarly, for all other vehicle fuel types, we exhibit this behavior. This table basically represents the SCR model, spatial autoregressive model results, and it summarizes the coefficient estimates for the spatial autoregressive model for various vehicle fuel types and US brand vehicles. The SCR model results shows that the county population has a statistically significant positive effect across all vehicle fuel types, suggesting that more urban counties have higher adoption rate for these vehicles. And median household income correlates with the adoption of these alternative vehicle fuel technologies positively. These results basically suggest that the incentives and subsidies given to lower income households may encourage adoption of these vehicle fuel types. Similarly, if we look at the state grid carbon emissions, we see that it positively correlates with the adoption of alternative vehicle fuel types and negatively with the US brand vehicles. And the negative coefficient associated with the weighted network travel time indicates that individuals with longer commute times are less likely to adopt PEV or fuel cell electric vehicles than US brand vehicles or hybrid electric vehicles. This result may be due to the range anxiety or the consumers perceiving internal combustion engine vehicles as more reliable option for longer commutes. Then we have also looked at the direct and the indirect effects of the SAR model. So basically, direct effect here represents the impact of each variable on the dependent variable within the same spatial unit, which is the county in our case. So direct effects are primarily relevant for local policy interventions within a given area, whereas the indirect effect represents the spillover effects, which means that the impact that changes in each variable have on neighboring spatial units. And the indirect effects are crucial for policies that affect the neighboring areas, showing that how intervention in one area impact the other through spatial linkages. So the results presented in this table reveal how various demographic factors, environmental awareness, and economic conditions contribute towards shaping local preferences, but also regarding the pattern it generates in the neighboring counties and the units. I won't go into the depth of these coefficients because as we have already discussed it together in that SAR model previous table. So I will jump on to the policy perspective that we have drawn from these results. So we have recommended that there is a need to promote the regional infrastructure development, and if we want to enhance the plug-in electric vehicle and the fuel cell electric vehicle adoption, as it has been evident by the strong spatial spillover effects, and to encourage the adoption of these vehicles, multi-county collaboration in infrastructure deployment and supporting policy is suggested to maximize the regional impact of such investments. And there is also a need to address economic barrier in minority communities. By addressing the economic barriers in minority communities, as the negative effects associated with high minority populations indicates the potential socio-economic barriers to these adoption of these alternative vehicle fuel types. So there may also be cultural factors that are not fully captured in the model. So solution might require targeted infrastructure investment or outreach programs in such communities. There is also need to leverage environmental concerns because we find high adoption of plug-in electric vehicle in states with high equivalent carbon emitting electricity grids. It is necessary to transition these grids towards renewable and low emission generation sources to maximize the environmental benefits. Thank you. And if you have any questions, please you can share it in the chat box, and I'm happy to answer those.
Thank you, Hania. Thank you. So, what questions do you have for Hania? So we have one question in the chat box.
Yeah. So there is one question by Purya, in which he or she is asking that did you consider any variable that captured the word of mouth marketing effect in the diffusion? Perhaps some of the spillover variables you mentioned may reflect that dynamic. Yes, you are right, but we have not considered those in our research because this was purely on the secondary data that we have got from the Experian Inclusive and the American Community Survey. So we have not considered those. Thank you.
Thank you. Thank you for the great presentation and great work. If there is no other question, we can go to the next presentation on the exploring online delivery patterns and returns insight from the 2022 National Household Travel Survey.
Okay, my name is Adedolapo Umbiri. I am a current PhD student at the University of Arkansas, and today I'll be presenting a study on online delivery patterns and returns using insight from the 2022 National Household Travel Survey. My advisor is Dr. Shuman Mitra, and I'll start off by just introducing us to a little bit of background on why this work is important. From the charts that we can see on my right-hand side, it shows the increasing number of people that have been engaging in some form of online shopping. And particularly of note is the impact of the pandemic on the number of new people that would be using it during, particularly when there was a lockdown. And of course, this is expected to form some sort of shift in logistics. That is how this shopping items are being delivered to individuals, as well as how it interacts with their actual travel themselves. In addition to this, there is not so much work around on the national level, how different people behave according to different categories of items that are being purchased online, as opposed to just looking at the general overview of items being ordered online. And the main objective that we try to do on this work is to explore online shopping based on their categories within the United States, as well as to characterize those that are engaging in returns, making use of the 2022 National Household Travel Survey. Just to better understand this particular study, I've included a couple of literature based on what has been done in the past. Now, there has been a couple of studies that has been done making use of a very similar data set, but before the pandemic, the 2017, the 2009 National Household Travel Survey, and there has been a couple of interesting results that has been found. Some of them include the fact that those that come from high income household, people who have more adult females within their household, and those that are highly educated were observed to have way more number of online shopping deliveries done. Also, there has been this reduction in disparity between factors that actually influence online shopping over time, particularly a study that was done comparing the 2009 National Household Travel Survey and 2017. There has also been a study that validates that there is actual differences between how people behave depending on the type of product that they actually tend to purchase online. And lastly is the research that shows increasing behavior of people making returns on items that are purchased online, which could be attributed to increasing flexible return policies by online retailers. Looking at the data that was used for this study, like I said, we made use of the National Household Travel Survey, the 2022 data set. This is the first National Household Travel Survey within the United States that actually collects data based on the particular categories and types of items that were purchased online. It was also the first to detail out how people are making returns based on their online purchases. In total, the total observation that we received from the data is about 17,000. Now, a lot of people that are familiar with this data set would agree with me that this is a lot less than the usual past historical household surveys. After cleaning, we had about 14,500 observations, and the data collection period is between January of 2022 and January of 2023. On the average, there is about 5.27 deliveries for each individual that's considered, and a distribution of the number of packages that each person receives is shown in this chart, showing that between 1 and 5 number of deliveries is what people would normally receive every month. Now, based on the categorization that was done within this data set, 4 main categories were highlighted. First is the food. This refers to the ready-to-eat meal that is being purchased online, groceries as well, and the goods category. This is a much larger category, and it's quite broad. And last is the services that are being ordered online and done in the individual's home. Now let's talk about the variables that was used for this study. For the dependent variables that we considered, we looked into the delivery count, the number of deliveries that each individual had received within the past 30 days, as well as what is the category of the item, and what is the number of returns, that is, if the individual engaged in some form of return in the past 30 days or not. And for the dependent variables, based on the availability of data within the National Household Travel Survey, we made use of the demographics, that's the gender, age, race, among others. Also household level information like the number of vehicles and household composition, the location, if it's an urban or rural, or the size of the metropolitan statistical area. Also, the kind of work arrangement that they have. Do they work from home or do they work in person? Or how frequently do they work from home? And their mobility impairment as well. In terms of modeling, we made use of majorly two models, the zero-inflated negative binomial. Now, this is validated based on past studies that has been done using a similar data set, and also the analysis of the data we found over dispersion within the data sets, having very high variance compared to the mean. And this would help us to be able to segregate structural zeros from non-structural zeros. We also made use of the logist model for the categories and the result of those engaging in returns. Now, this particular work was carried out using Stata 16, and I will just go ahead to discuss some of the key findings that has been summarized here for this presentation. Now, in terms of the general number of deliveries that are being made after the pandemic, how has it changed and what is the state now? We found particularly those of the millennial generation and the Gen X to have a higher number of deliveries compared to any other generations, which kind of shows a nonlinear relationship, as we have the Gen Z who are lesser in age, and also the older individuals having comparatively less number of deliveries. Those that frequently also work from home were observed to have a higher number of deliveries than those who do not work at all, or those who work 5 days at the office. The highly educated were also observed, and the higher income, which is very similar to what has been reflected before the pandemic. The mobility impaired individuals were also observed to have a higher number of deliveries being done than others. In terms of the urbanicity of the area, we found no statistical significance in the differences amongst how people, the number of packages that they receive at home. Now, in terms of the categories, I'll take this one category after the other. The first is the food category. Now, the first thing that I like to note is while the urban-rural indicator showed no significant statistical difference, we do found that more likely than not, people in the urban areas would usually engage in purchases of their food online, which kind of shows the need to kind of break down items as opposed to just taking a look at the number of deliveries that people are doing when it comes to understanding their travel. Also, people who work from home frequently would usually engage in this type of purchase. The mobility impaired as well. And in terms of age, there is just this linear relationship based on generation that just reduces. The older generations would have a less likelihood of purchasing such category of items online. And when it comes to groceries, we also have the urban-rural indicator having a statistically significant result, showing that people in the urban areas still have more likelihood to engage in this type of shopping. The mobility impaired as well, they have a higher likelihood, and those of the female gender. In terms of age, we had this non-linear relationship where the millennials were observed to more likely than not be the group that actually engages in this form of online purchases. And when we look at the general category of goods, now this is a little bit broad, and it's contains different merchandise and other items that are being purchased that could not be classified as the other ones. There is this linear relationship in terms of the age. The older generations tend to order more of these kind of categories whenever they do make their online purchase. In terms of general population within the United States, there is less likelihood from the minority ethnicity groups to actually make purchase of this particular category. The highly educated tend to have more purchases of this, and those that live and are resident in the more rural regions tend to have more purchases of this category as well. Now, when we look at the services category, how do people purchase online services which are being done in their home? We see and find some interesting results, such as people who do not work kind of tend to have more of this type of online purchase done. Also, in terms of education, there is a non-linear relationship, and interestingly, individuals with associate degree or less are more likely to make this kind of purchase. The mobility impaired were also found to have a higher likelihood. And in terms of the general US population, the minority ethnicity tend to find more use for this particular type of online purchase. And when we look at the returns in general, who are those that are more likely when they make these purchases to make a return? In terms of education, the highly educated were found to have a higher likelihood than not. The age, we have the generation X and Y to have a higher likelihood of actually making returns. And in terms of gender, we have the female. When it comes to the resident location, there is no statistically significant results that was found within the urban and rural areas. However, we found that people that tend to live in a bigger metropolitan statistical area more than not have found to have a higher likelihood of making such returns. And what are some of the practical and policy implications that we have found so far? First is the reoccurrence and the emphasis on the mobility impaired individuals across different categories. They were found to actually have more use for this online shopping activities. Also, retail outlets could gain better insight, particularly in terms of the returns, as to who are those that are making returns across a national level, and a better understanding on just how future policies could affect shopping behaviors and overall travel demand that comes as a result of this. And what are some of the study limitations as well as future research? First is the lack of attitudinal and perception variables. Some of the past studies have shown that these very type of variables kind of also influence how people make their online purchase decisions. Also, the fact that we have a very broad category, which is the goods, which also has a very higher percentage of the number of the overall deliveries that was made. It would be interesting to see if these could be grouped into subcategories and try to understand what dynamics goes on within that as well. And some of the feature research are like gaining more insight into travel relationships based on each of these individual categories, and also further exploring returns based on what kind of items are these people actually purchasing online. And just to close this presentation and as a conclusion, we found overall that the majority of the trend still follows what holds pre-pandemic, although the disparity is kind of increasing as opposed to what was found before. It's still being the fact that online shopping is still being strongly characterized by the individual, their demographics, and there could be future research and policies into what are the environmental impact based on the continued trend that we are observing. And if you have any questions, feel free to reach out to us through this email. And if you have, you can also ask me any questions right now as well. That'll be all from me.
Thank you for the great work. So, any questions? So we have one question in chat box. Did you look at the decrease in shopping?
So I'm assuming by decreases in shopping, you refer to like decrease in in-person shopping. For this particular part of the study, I would say no. So this is a part of a larger study that we are carrying out. There's a different part where we also like look into the interaction with in-person shopping. But up here, we're just trying to understand who are those that are actually that are actually making online purchases.
Okay, if there's no question, we can move on to the next presentation on a street view-based automated walk audits near public transport station in the global south by Juan.
Hi, I'm Uriel Legaria. I'm going to present my work, which is called Street View-Based Automated Walk Audits near public transport stations in the Global South. I'm currently working at the Center for the Future of Cities at Tecnológico de Monterrey in Mexico. And I want to thank my collaborators on this work, who were Roberto Ponce Lopez, Runak Pasu, and Joseph Ferreira. Okay. So the areas around transport stations are key in shaping the perceptions of people towards walking in cities. This is because many people have to walk regularly in these areas as part of their daily schedule. They walk by necessity. So it has been emphasized that it is important to ensure that you have an adequate infrastructure in these areas that supports walking and that ensures the safety of pedestrians. And a question related to this is how can we evaluate walkability at an area or the walking conditions in an environment? And traditionally, the main approach that was used is that you would see this as an accessibility problem. So you would evaluate if you could reach the station, if you could trace paths along the street network towards the station for pedestrians. But if you zoom in on these trajectories towards the station, you see that reachability is not the whole story. Because features that you observe at a street level also matter. The conditions of the streets, whether you have vegetation, whether there are obstacles, all of these things are important for shaping the perception of pedestrians. And so AI has opened the possibility of detecting these features that are important for walkability and which we can see in street view images. There are some walk audit systems that have been developed, particularly in cities of the global north, in cities of the US and Europe. What these systems do is they focus on an area of analysis. They obtain street view images on this area, and then they detect using AI the different features that can affect walkability, so vegetation, the presence of sidewalks. There are many things that you can detect. And the question remained of whether it was possible to adapt these new technologies to different contexts like Mexico and India, where urban form might be different, and also the factors that affect walkability might be also different. So our objectives for this project was first to implement an automated walk audit systems focused on Monterrey, Mexico, and Mumbai, India, and apply this system to 4 transport station catchment areas. So we chose 2 stations per country, 1 high density and 1 low density. For Monterrey, we picked Cuauhtémoc, which is located in the downtown portion of Monterrey, and San Nicolas Station, which is located at a peripheral municipality of San Nicolas. And for Mumbai, we chose Andheri and Ghatkopar. While both of these have mixed use, Andheri tends to see a little bit more commercial activity. Okay. So for implementing our systems, what we did first was explore the spatial coverage of street view imagery services. we focused on Google Street View and Mapillary, which is open source and where the images are contributed by users. We compared the stations in Monterrey and Mumbai with stations in cities of the global north, like Boston, Singapore, London, and Seoul. What we found was that, so what I'm showing here is the percentage of streets where we found images around the stations, and the radius we used was 600 meters, which is the value that is recommended in the literature. So we found that the coverage offered by Mapillary tended to be lower for the global south stations in comparison to some of the stations in the global north. For Boston and Singapore, it was close to 100% the coverage. So this map, I showed this map to emphasize that point. It shows the coverage for the Andheri, around the Andheri station in Mumbai, for Mapillary and for Google Street View. The purple segments are the ones where you could not, the system could not find images. And you can see that there are a lot more uncovered segments with Mapillary in comparison to Google Street View. So this led us to define Google Street View as the data source that we were going to use for our system. And next we studied how recent were the images provided by Google Street View. So this shows the percentage of images around the stations that have been updated in the last 5 years. And we found that for the 4 stations in the global south that we were interested in, the percentages tended to be reasonably good. They tended to be above 80%. The lowest, the oldest images were found in low density station areas of the global north, for instance, Amersham in London. So once we had validated our data source and the time relevance of the data, we next explored whether it was possible to transfer some of the models, AI models that had been pre-trained on the global north, whether we could use that with our data. We found that particularly for building segmentations, the system tends to underperform because it cannot detect very well like informal settlements or buildings that where the construction was started but it was never finished, which is common enough in Mexico. So what we did was we trained our own model with images collected from Mexico, from India, and other countries in Latin America. And we found that performance went a little bit up with that. This is the intersection of our union. We compare the model trained in the global north, which is the purple bars, with our model, which are the green bars. And you can see that performance is a little bit higher for detecting and segmenting buildings with our model. An additional adaptation that we made was detecting informal retail stalls. So these are stalls that you can find clustered around the stations, usually in Mexico and India. When they are well placed, they can attract the attention of pedestrians. But what happens often is that they block the streets or the entrance to the station. And this creates unsafe situations because sometimes pedestrians need to get off the street to access the entrance, and it is unsafe for them. So we trained a YOLO model for detecting these informal retail stalls also. This is our final systems and the steps of operation of it. We first retrieved the the street network around the station. We used a 600-meter radius. And we distribute points where we will collect images. We distribute these points at regular intervals along the streets. Then we collect the images. We collect the sidewalk views at each point. And we apply the segmentation models to detect things like sky, vegetation, buildings, the informal retail stalls, persons, the sidewalk, streetlights. And then we can map the presence of these features back. So I'm showing here the number of retail stalls that were detected in each of the streets. And the purple ones are the ones where most informal retail stalls were detected. And we have a whole set of features that we can obtain, like person counts, building counts, green view index, sky view factor. We also have a method for estimating the heights of the buildings in meters. This uses projective geometry. And there were some features that we do use the model trained in the global north. And this was the case for sidewalks, crosswalks, streetlights, and walk signals. So this is a summary of our results. What I'm showing here is the average values for the features for each of the stations. We found that the system is able to tell some information about the ecosystem around the station. For instance, it was able to detect that in Monterrey there is a high sky view. This is because of this desert ecosystem of the region. It also has low vegetation. It was able to distinguish between the low density station and the high density station. So you can see that, for instance, in Cuauhtemoc, which is the high density stations, you have more building counts and more informal commerce and more streetlights. And also for Mumbai, in Andheri, we detected a lot more informal retail stalls and buildings. One particular feature that the system failed to detect was crosswalks, and we realized this later on. This is due to the way we are distributing the points where we collect the images. We mainly distribute these points in the inner portion of the streets, and we are ignoring the intersections, which is where you are more likely to find the crosswalks. So this is something that we plan to fix in our system. We compare these metrics that we obtained with our system with ratings that were obtained on site from pedestrians. So we applied a survey, which is part of a larger project. And some of the questions in that survey focused on evaluating different infrastructure elements. So the respondents would give a rating from 1 to 5 to sidewalks, crosswalks, shadow and vegetation, storefronts and amenities, and street lighting. We found that in some cases, these perceptions align with what we obtained with our system. For instance, in the case of sidewalks, people in Monterrey do tend to rate a little bit higher the sidewalks than in Mumbai. And we also detected more sidewalks in Monterrey than in Mumbai. In other cases, it does not reflect, our system does not align with the perception. For instance, for shadow and vegetation, more vegetation is found in Monterrey. But here, people rated it lower. And this is because we are merely focusing on capturing the presence of the vegetation, but we did not obtain other information such as the shading it provides, which it is important because you can detect a lot of vegetation in Monterrey, but it does not usually provide good shading because of the desert ecosystem of the area. So as final experiment with our system, what we did was explore the correlation between built environment features and ridership. We found that, as one could expect, the number of persons that you detect in the images is correlated to the ridership. This was something that we corroborated. Another relation that we found for both countries is that the number of retail stalls of informal commerce is correlated with ridership. You tend to find more of these informal retail stalls close to the station. For instance, here in Cuauhtemoc, this map shows the color map is the number of retail stalls, and the ridership is given by the size of the marker. So you see that in Cuauhtemoc, you have a high number retail stalls around the streets, and also a high ridership. It is positively correlated, and it showed a statistical significance also. So the conclusions, the system was able to give us some information, like distinguishing between the high density and low density areas. It also is able to say something about the ecosystem that you will find in an area. And it also tells you some information about urban form, because we are also obtaining building heights. But it does not align, well, it aligns with perception in some specific cases, like sidewalks. There are others where the ratings given by pedestrians did not align with what we obtained with our system. And this developing the system allowed us to explore how the built environment variables scale with ridership. And we found that informal retail stall counts are correlated with ridership. To improve our work, well, one thing that we will improve in the short term is the detection of crosswalks. And we also want to explore detecting details, not only presence of the elements we are detecting, but also the details of them. So the type of vegetation maybe. And we want to explore using LLMs for this purpose, for obtaining this complex information. Yeah, that's it. Thank you.
Thank you, Juan. Is there any question? Thank you. Thank you again for your presentation. So we are going to the last presentation by Puya Parsa on video-based vehicle surveillance in the wild, license plate make and model recognition using vision language models.
Awesome. Thank you, Mohammed. Hello, everyone. My name is Puya. Please, could you tell me that if you can see my screen?
Yes, we can.
Okay. Awesome. The title of our paper is Video-Based Vehicle Surveillance in the Wild. In the wild, license plate make and model recognition with self-reflective vision language model. This is a collaboration between University of Minnesota and University of Texas at Austin. For the motivation part, first we should take into consideration why we need such a system. And let's look at the numbers. 1.2 million road traffic deaths worldwide, and 40,000 of them happened in the US in 2003. And the main cause behind those deaths are speeding. So one of the solutions is just install speed camera sites everywhere. But the problem is that they're going to be costly, and on average, one single camera site is going to cost around $120,000. And most of the agencies trying to install these camera sites, they have partial coverage. And even though if we can install camera sites everywhere, there's going to be something called as a kangaroo effect, which is something related to driving behavior. The driver knows where the camera site is, so it's going to slow down. And after passing the camera site, it's going to speed up. So they're not going to be effective after like a definite span. There are some solution into this problem, and one of them is crowdsourcing videos. So right now, worldwide, it's happening in South Korea and New York. So you can see two examples here. On the left, you can see citizens in South Korea, they can report a driving violation, and they can get some monetary reward in return. And on the right, you can see an example in New York City when a citizen can upload 3 minutes videos reporting a truck parking somewhere not comfortable or causing traffic. But the problem one of the challenges these crowdsourcing videos are facing is that most of the time there are these forms that users have to fill out, like license plate, model, make and color. And most of the time it's going to be discouraging for the users to fill out this information. They might not have clear vision on the license plate, and this is going to be discourage the whole system to work. And you can see here an example how a license plate might look like in a footage. So on the left side, you can see an ideal license plate, but on the right, this is what happened in reality. So the research question and our contribution is that can modern vision language models can replace all these traditional pipelines that are currently working. For example, there are dedicated OCR engines for license plate. There are CNN models for make and model detection. There are a lot of systems separately working. But we are thinking about replacing all those systems with vision language model systems. And you can think of vision language model as something like ChatGPT, which can accept text and image at the same time. It can process it and spit out some information. So our key contribution is we proposed 2 different pipelines for license plate and make and model. And we provided some zero-shot benchmark on 4 recent VLMs on make and model and license plate. We also introduced a lightweight self-reflection module that can add robustness to the prediction happened by VLMs. Here you can see the pipeline proposed for license plate. As you can see, there's an input processing module and there's a VLM querying part. In input processing, we are trying to come up with the best frames in a video. As you know, a video consisted of maybe thousands of frames. So we have to be very selective with those frames. We have to pick the frames with the best quality to read the characters from license plate. And after that module, we have the input to VLMs. So we come up with these frames, we combine it with some textual prompt. So we have a multimodal prompt, and we can ask our VLM to predict something for us. For the make and model, we have the same module as license plate, but we also propose an optional module, the self-reflection module here. So there's going to be some details around the self-reflection module, which we're going to dig into in later slides. But as you can see, we have a database crawled from the web consisting of different make and models. So once we have a query image from a car, we can retrieve an image from a database we have we can combine those images together and we can reassure that the first prediction by our VLM is correct. If not, we do some kind of self-reflection and we can refine that prediction one more time. So about the input processing module in license plate, you can see we are using two different image quality metrics, namely clip IQA and BRISC. You can see that the scores by the clip IQA and BRISC bring up the better quality. So the lowest scores and the highest scores here, you can see that the lowest scores hardly we can read the characters, but the highest scores are more visible to human eyes. So we assume that the VLM is going to have an easier job to predict the characters. For the evaluation, as I already mentioned, for license plate, we consider 24 different configuration for license plate. We are testing around among 4 different VLMs, namely GPT-4o, Llama 3.2 Vision, Lava, and Mini CPM. For prompting, we have 3 different prompting strategies, single call, 3 options, and 3 calls. In single call, we are asking the VLM for the best prediction. In 3 options, we ask VLM to come up with the 3 most possible predictions. And in 3 calls, we are basically doing the single call for 3 times separately. And we show that some of the time, this makes a huge difference, although they might seem similar to each other, but these strategies bring up different results. So here is the number, here is the table for the license plate recognition results. As you can see for the single call strategy, you can see that the numbers for GPT-4o and Llama 3.2 Vision are much higher than the other 2 VLMs, which shows the capacity of different VLMs is going to affect the accuracy by a lot. And when we are comparing the different strategies, we see most of the time 3 calls is going to be most effective. So 3 calls bring us almost the highest numbers in this table. And the interesting thing is that comparing this number into the baseline. So baseline reported by Leah et al. Is around 46%. But if we kind of like replace the kind of like the traditional models by kind of like non-VLM methods versus VLM methods, is going to have a huge difference in performance. About the self-reflection module that we discussed earlier, here you can see 2 examples. So here is the query image that I was describing at the beginning of the figure. And here you can see the ground truth make and model of this car. Here is the prediction, the first prediction by VLM. And here is the retrieved image from the database. After we are prompting again the VLM to kind of review the first prediction, you can see it was able to correct itself and come up with the right prediction. Here is another example for another car, but it's pretty much the same thing. At the beginning, it was the first prediction was Renault Sandero. And once we retrieved the image from the database for this prediction, the model find out maybe the first prediction wasn't right. So it tried to correct itself to Ford Fiesta. So here you can see how the self-reflection module is going to affect the numbers over different VLMs and different datasets. Here is the dataset for smartphone videos, which most of the time there are not fixed cameras, going to be shaky. And UFPR is kind of in between fixed cameras and moving cameras. It's a camera mounting on the vehicle that is moving. But although the datasets are different and the VLMs are different, GPT-4o and Llama 3.2, you can see that we see consistent improvement on the numbers. So on average, we can see 5% improvement in prediction accuracy for make and model. So we claim that this self-reflection module is going to be an optional module that can improve the robustness, while it adds some kind of cost into the inference. There's going to be some consideration about the cost and deployment. First of all, GPT-4o is a proprietary model, and we were running the inference via an API, which is going to cost us per API call. It's negligible for a low number of samples, like 24 or 59 samples. But as we are doing this as a scale for millions of inferences, this number is not going to be negligible. So people that are doing this as a scale has to consider the costs. And the interesting finding in our paper is that Llama 3.2 right now is open source, and we were running it on our GPU servers. And it was we got the same result at GPT-4o, which is a very good news to open source community. So as I told you, we were running our pipelines on RTX 6000. But if you are doing this on edge devices, there's going to be quantization and pruning necessary for making this possible on edge devices. For conclusion and next steps, so one of our main takeaways was that VLM-powered zero-shot pipeline is going to beat the specific models on noisy videos. And the self-reflection is very general, very generic. It can be applied to many pipelines. And it was shown that it's consistently helpful among different VLMs and different datasets. The limitation of our work is that we are depending on frame quality. Like most of the video taken in this paper are by iPhone 12, which is like still high in quality. We don't know what happens if the quality of the frame degrades. And we are not dealing with rare license plate font that happens around the world. We are working with common license print formats. And right now, we are doing all the processing on the GPU servers that we have. So we don't know what happens if we do it on edge devices like mobile phones. There's going to be some latency issues, but we haven't do that on edge devices. So for our future work, we're going to focus on on-device optimization like pruning and quantization, which makes the models faster, but we don't know what happened with the performance. We're going to extend it to more a variety of license plate scenarios like international plates or commercialized plates. And we're going to add more complicated self-validation method, like the self-reflection I mentioned, but it's going to be more complicated. And thank you so much for your attention. And I hope you had a nice day. I'm here for any question if you have. Thank you.
Thank you, Puya. So, what questions do you have for Puya?
Okay, let me look at the chats. So, I mean, right now, can you read the question to me? I'm not able to find it.
Do you plan on testing edge devices?
Yeah, it's gonna be in future work. We haven't did it yet because right now the RTX 6000 is not gonna be comparable to the resources that you have on an iPhone. So there's gonna be some pruning. You have to make the model much more lightweight, but we haven't did the experiment yet. My pleasure.
Any other questions for Puya? Thank you, Puya, for the great presentation. So thank you,
pleasure.
everyone. I believe that we can adjourn this session here. Thank you for attending this nice presentation. Hope you have a great rest of the day.